Session 2, Out of the Box Ideas for Innovative Policies and Programs, aka Big Challenges and Big Solutions. I have a few housekeeping items you guys have heard a couple of times in our last session, so I'll keep it brief. First, I'd like to thank our sponsors for making this event possible. DT, especially the host sponsor. If you'd like to learn more about them, please visit the sponsored link on the left-hand column of your page and visit their website to learn more. We have an exciting lineup of speakers today, and they'll do the presentation first. And we'll have the last 15 minutes of the session to ask the speakers any questions you guys have on their presentation. If there are questions remaining unanswered, ACEEE will collect them and send them to the speakers for response after the conference. With this being in mind, you can see a chat box on the right-hand side of your screen. Please use this to ask questions of the speakers and refrain from engaging in conversation with one another. If you'd like to connect with the attendees, you can do so with using the attendee links on the left-hand column, and you can see any attendees who have a profile that's been created on the site. You also have attendee resources. The resources contain program proceedings, attendee list, and an evaluation. Should you complete one with your name and a testimony, you could get a discount on your 2023 summer study. The program participant link also has today's presenters' bios and copies of their presentation if you'd like to access them. And lastly, please join us at the end of the day for our post-panel debrief, where you can actually catch up on discussions you might have missed. And remember, all these sessions are video recorded for your access on demand later on after the conference. Now let's get started with our speakers. First speaker is Andrew Hoffmeister. A little about Andrew. He's going to be speaking to us about the role of state policy in furthering industrial decarbonization via energy efficiency. Andrew is a program analyst on ACEEE's industrial team. His work focuses primarily on decarbonization policy research, messaging, and outreach. Prior to joining ACEEE, Andrew volunteered at the Tennessee Department of Environment and Conservation and conducted research on decarbonization planning. He holds a bachelor's degree in Earth and Environmental Science from Vanderbilt University. Andrew, if you're ready, the floor is all yours.
Hi, everyone. So as you mentioned, my presentation is about the role of state policy in furthering industrial decarbonization through energy management and industrial assessments. So a recent state assessment examines the potential of continued and expanded industrial energy efficiency, or IEE, policies and programs to reduce North Carolina's annual energy demand and help reach state-level climate goals in the electric power sector. And I wanted to expand upon the sections of industrial efficiency published in that report and relate the ideas to other states' perspectives using North Carolina as a case study. My goals were to look at the role that industrial assessments and strategic energy management specifically can play in state strategies for mitigating emissions from the industrial sector, along with policy choices for maximizing that potential and how existing federal, state, and local infrastructure can be leveraged in North Carolina and beyond. So 33 states have either released climate action plans or are in the process of developing them. These plans include approaches like resilience strategies, economic goals, including recovery and job creation, social goals, and clean energy targets. North Carolina is one of those states, having developed its clean energy plan in 2019. The plan has strategies as to how to reach a greenhouse gas reduction target of 40% by 2025 by decarbonizing the electric power sector. When within that electric power sector, North Carolina wants to reduce its GHG emissions by 70% in 2030 relative to 2005 levels and reach carbon neutrality in the sector by 2050. Figure 1 here shows the emissions at a 2005 baseline, the GHG reductions from the continuation of existing efforts in the reference case, and the potential for new EE measures, including industrial energy efficiency, to help North Carolina reach its emissions targets. So improving energy efficiency in industry is an essential way to advance decarbonization, reduce electricity demand, and provide cost savings to integral parts of state economies. And this is especially important, just I'll note, in light of the relatively cheap cost of saved energy in the industrial and commercial sectors and the energy intensity of those sectors. North Carolina industrial customers were responsible for over 27,000 gigawatt hours, or about 20% of North Carolina's electricity consumption in 2018. And those numbers are represented here in Figure 2. Using state and federal funding to leverage existing programs and to reinforce existing offerings of technical assistance, energy audits, assessments, and energy management is essential in maximizing the potential of industrial savings in terms of helping North Carolina and other states reach their climate goals. So North Carolina utilizes several university, government, and nonprofit programs to provide energy assessments and technical assistance to the industrial sector right now. This includes the Local Industrial Assessment Center, or IAC, at North Carolina State University, nonprofits such as Advanced Energy, and governmental entities, including Waste Reduction Partners and the North Carolina Clean Technology Center. So the DOE-funded IAC performs energy use assessments for industrial customers and are critical to expanding industrial EE. These centers and their assessments provide industry-specific expertise and help to create a knowledgeable workforce for industrial transitions. They connect small and medium customers with energy savings opportunities, as well as quantify potential energy and cost savings. So there are opportunities to leverage those benefits of industrial energy assessments through additional state and federal funding on top of the funding that the Department of Energy already provides. So in that state assessment, we calculated that industrial assessments in North Carolina can save over 200 gigawatt hours of electricity in 2040. Since 1992, the NC State IAC has conducted over 500 assessments, implementing over 1,800 voluntary energy efficiency measures and saving almost $25 million. Since 2012, about 67 recommendations have been implemented each year, with average savings of 124 megawatt hours per recommendation. So along with the other sources of energy assessments, those continuing existing efforts from those other sources, that would result in about 36 gigawatt hours of savings in 2030 and about 50 gigawatt hours of savings in 2040. So if North Carolina were to double the current IAC funding, we found that the number of implemented recommendations and resultant savings could also double, reaching 100,000 megawatt hours of savings in 2040. So combined with those existing efforts above, it's possible to reach savings of 176 gigawatt hours in 2030 and 208 gigawatt hours in 2040, or 0.1% of the total electricity load in 2040. So the NC State IAC could also deliver significant peak savings by helping industrial customers change rate schedules, reduce loads, and shift plant operational schedules. Also, there's the potential for further savings through a new IAC at another major engineering university in North Carolina or nearby, and complementary policies that would operate to reduce industrial energy consumption include support for smart manufacturing and intelligent efficiency, and any training and grants that could help further systems optimization, increase flexibility and data coordination to reduce waste materials and energy losses to complement those industrial assessments, as well as any federal legislation that would increase funding to IACs, create new IACs or centers of excellence, expand the scope for assessments, increase the size of centers, or incentivize implementation of recommendations that would all significantly contribute to new savings. So next, moving on to strategic energy management, or SEM, which achieves systematic energy performance improvements by empowering organizations to manage energy use consistently and effectively. Continuous energy saving improvements are furthered through technical assistance geared towards identifying and prioritizing energy saving methods and supplying that kind of hands-on support. SEM involves a commitment to energy management, planning, and implementation, supported by a framework of measuring, reporting, and verification. And statewide SEM programs have significant potential for energy savings. In fact, programs often report savings as high as 10% of annual energy spending for participants. So there are existing SEM programs in North Carolina already, as with the industrial assessments. Several programs and approaches support SEM and similar practices in North Carolina. State offices, including the Department of Environmental Quality, or DEQ, as well as third-party organizations, federal offerings, and industrial customers that have established and report on their own energy savings goals, have helped the industrial sector make significant strides towards EE improvements through energy management. So that current participation includes North Carolina's, the DEQ's Environmental Stewardship Initiative, 10 facilities which are already using the 50,001 Ready Navigator tool to track the progress of their energy management systems, Advanced Energy, which is currently hosting an industry cohort using the ISO 50001 Ready program, and the Utility Savings Initiative, which works with the UNC system, community colleges, and state agencies to educate the need for strategic energy planning and other management programs. So despite progress, there is potential still there in North Carolina. Approximately 99% of the estimated eligible industrial and commercial demand for 2020 has not participated in those voluntary programs. So if North Carolina's DEQ were to launch a statewide SEM program that would aim to target medium and large industrial and commercial customers that have the ability to opt out of their IOU service provider's EE rider, savings could be captured that would otherwise be just out of reach by existing entities or measures. Opt-outs in 2019 accounted for approximately 32 million megawatt hours from commercial and industrial, or about 52% of the total sales to those sectors. And the potential SEM program we analyzed would aim to capture savings from those customers, as well as support programs that cater to small and medium-sized companies, as well as the efforts of DOE through their IACs, Superior Energy Performance Certification, ISO 50001 Ready, DEQ's programs, and third-party and other utility offerings in the state. So a statewide SEM program we found has the potential to enable average annual electricity savings of 420 gigawatt hours from 2022 to 2040 in North Carolina, reaching annual savings of 500 gigawatt hours in 2030 and 591 gigawatt hours in 2040. So these savings would add to the existing efforts of DEQ's Environmental Stewardship Initiative program for combined savings of over 1,000 gigawatt hours in 2030 and over 1,200 gigawatt hours in 2040. So there are additional potential savings that are possible through the cohort model, such as the one being developed by Advanced Energy, or through SEM continuation after the program's first year. Additionally, participants can opt to have new sites from their organization participate, which would expand the potential savings. There are also further savings possible beyond the scope of what we analyzed if participants establish standalone internal energy saving procedures after they participate in SEM programs, or if participants adopt SEM practices at other non-participating sites. And some additional potential savings could come from customers of co-ops and municipal utilities who could participate in a statewide SEM program, which were not captured as part of this North Carolina analysis. So similar savings are possible beyond the scope of North Carolina. So the above energy efficiency approaches in North Carolina have that potential to help save over 1,400 gigawatt hours of electricity in 2040, which is 2% of forecasted IOU C&I sales in 2040, which would be about 480,000 metric tons of carbon dioxide equivalent, or 0.6% of the 2005 baseline that we looked at earlier. And with both approaches, there is opportunity to pursue even more aggressive savings by increasing funding to the mature NC State IAC, creating a new IAC in North Carolina or a nearby state, funding additional SEM cohorts, in addition to further savings beyond the scope of the analysis. And in other states, not only in the Southeast region, but across the US, there's a similar landscape of opportunity within reach. Existing programs, especially SEM and industrial energy audits and assessments, can be leveraged, funded, and expanded to reach new targets in the industrial sector and provide enhanced energy efficiency possibilities to help states reach their climate goals via savings in the electric power sector. So there are many examples of opportunities of programs to leverage across the US. On the SEM side, first of all, in Colorado, the Colorado Energy Office's Industrial Strategic Energy Management Program offers direct organizational and technical support from experienced energy managers and coaches to industrial customers which helps companies establish energy management plans, energy reduction goals, and low-cost EE improvement measures. In New York, NYSERDA offers training options to teach businesses how to establish and implement SEM through continuous measurement and improvements to energy performance and workforce engagement. And they also offer SEM on Demand, which is a remote learning training program that provides guidance and technical support to facilitate SEM adoption. And just a last example, in Vermont, participation in the Self-Managed Energy Efficiency Program is dependent on demonstrating a comprehensive energy management program. So these are just a few illustrative examples of a much larger landscape. So leveraging these approaches, as in North Carolina, examining opportunities for expansion, enabling connection with peers is really needed to move the needle on industrial energy efficiency and savings in industrial electricity consumption across the US. So continuing to support that cohort approach, peer exchanges, experience sharing, and other initiatives will be essential to furthering the potential of SEM. And SEM should be considered an essential strategy in state and local industrial energy efficiency portfolios because it has that potential to integrate EE policies such as benchmarking and disclosure and practices, including voluntary commitments to greenhouse gas reductions under a single framework. And strengthening funding to help implement recommendations and reach more industrial customers will likely help industrial organizations increase savings, as well as support states in reaching their climate and power sector decarbonization commitments. On the industrial assessment side, utility programs such as Dominion Virginia Energy's Small Business Improvement Program offers on-site energy audits performed by contractors, and state programs like the Massachusetts Energy Efficiency Partnership works with the IAC program to support industrial plants with technical assistance in implementing efficiency measures. So industrial assessment should be considered a low risk, low cost, relatively bipartisan method of reducing industrial electricity consumption with an existing EM&V framework that can start enabling more savings in the immediate term, especially paired with a policy emphasis on smart manufacturing. So just some quick conclusions. Industrial decarbonization can play a significant role in mitigating the worst effects of climate change. Industrial energy efficiency is a potential significant driver to that end, and individual states can play a critical role in leveraging existing structures at both the state and federal level, as well as creating new infrastructure that helps realize opportunities to reach as much of the sector as possible. Industrial assessments and strategic energy management are industrial energy efficiency strategies that can do both. There are many existing structures of energy management and audits. DOE's IAC program, for example, has delivered significant savings to the industrial sector for decades. And states like North Carolina have the opportunity to leverage that existing infrastructure, increase funding, create new programs, and increase collaboration to fully access the potential of industrial energy efficiency in reaching state-based climate goals. So thank you, and I believe we're having all questions at the end. Yeah.
Hi, everybody. We're going to move on to presenter number 2. The next presenter is Caitlin Swalek, who will present the topic of low carbon steel production transition through the lens of oil and gas industry. A little bit about Caitlin. She is an engineer and an energy and climate researcher at Global Energy Monitor, where she focuses on industrial decarbonization, particularly iron, steel, and hydrogen. She previously worked as an air quality engineer in compliance reporting and permitting for fossil fuel fired power plants throughout the United States. Caitlin also worked as a wind farm planner and analyst for Fraunhofer IWES and as a communication specialist for the National Center for Ecological Analysis and Synthesis. Caitlin received her bachelor's in chemical engineering from Worcester Polytechnic Institute, a master's degree from UC Santa Barbara's Bren School of Environmental Science and Management, and a TerraCore certificate for the New Hydrogen Economy. Without further ado, go ahead. Caitlin, it's your chance to present.
Okay. Thank you, Sadika, for that warm welcome. I'm very excited to be presenting here. As Sadika said, I am presenting on oil, gas, and green steel, industrial decarbonization through the lens of the oil and gas industry. So when we're talking about big challenges, I think this is a rather big one, and hopefully I'll be presenting some big solutions that we could also be looking at. So a bit of background, Global Energy Monitor is a global nonprofit research think tank that is building an open guide to the world's energy system. So we've mainly focused on building out asset level trackers for the fossil fuel industry. But we recently added steel as our first move into industrial decarbonization. We're also building out a renewable energy tracker, and we currently have trackers for the fossil fuel infrastructure, gas plants, coal plants, and coal mines. And each of these trackers provide plant or asset level data for ownership, capacity, location, trying to create data sets that bring more transparency to these industries, and all in an effort to move towards clean energy and industrial decarbonization. So I manage the Global Steel Plant Tracker at GEM, and this tracker has the largest, around 650 crude steel production plants in the world. The tracker is set up with three main pieces. So first, we have our online interface, which I'd like to just show quickly. There's two parts here. We have a dashboard that shows some data visualization and a tracker map that has all of the plants located. And in this capacity view, you can really quickly see some major trends in steel production. And I'll be getting into steel making and why this is relevant in just a moment. The few things to pull out here are, a huge concentration of steel production in China, mostly the blast furnace, basic oxygen furnace route, and that electric arc furnace steelmaking is the predominant form in the US. So the other pieces of the tracker, we also have a wiki page for each steel plant, which provides background information on the plant. It also provides a lot of detailed information that comes from our underlying database, which is the third piece of the tracker. And we currently provide data on location, ownership status, or operating status, the capacity and production of the steel plant, the steelmaking process, and then some details on the furnace units at the plant. And then we have additional data that we don't, it's not quite complete, so we don't release it publicly yet, but it includes information on steel products, sector end users, such as oil and gas, raw material sources, and then we're looking to expand the tracker by including more innovative, low-emission steelmaking projects, workforce data, and information on emissions. So when you're looking at emissions from the steel industry, it really depends on the process. So there are three main production routes for steel making. And I'm going to go over these briefly because it's important context for the rest of this discussion. The first route is the blast furnace basic oxygen furnace steelmaking route. So in this steelmaking route, the raw materials are coking coal and iron ore, and then some other things. And the coal and iron ore go into the blast furnace unit, or BF as we call it, and that is the iron making phase. You create pig iron. That's also the most emissions intense part of the steel making process. From the blast furnace, the pig iron goes into a basic oxygen furnace where it's made into crude steel. Overall, the emissions for the blast furnace basic oxygen furnace steel making route is approximately 2.3 tons of carbon dioxide per ton of steel. In the next steel making route that we're going to go over, this is direct reduced iron electric arc furnace steel making. And in this route, an important distinction is that the raw materials are iron ore and then some other things, but you don't have that metallurgical coal. So the metallurgical coal creates process emissions in the blast furnace basic oxygen furnace steel making route, which makes it really hard to decarbonize that steel making route. And that is the most common steel making method right now. About 2/3 of global production uses the BF-BOF route. Now, the DRI-EAF route, here you have the iron ore put into a DRI unit where it is reduced by a reducing gas, and that creates sponge iron that's then turned into steel in the electric arc furnace unit. The electric arc furnace, or EAF as we call it, emissions are really dependent on the electricity grid mix that you're using. But the emissions from that DRI portion really vary based on the type of reducing gas. So if you're using coal as the reductant, you can see emissions as high as the blast furnace basic oxygen furnace steelmaking route, even higher. But what's more typically used is natural gas-based DRI. And the emissions from that process are around 1.5 tons of CO2 per ton of crude steel. So about 2/3 what you have with the blast furnace basic oxygen furnace. The third route that's also commonly used is scrap-based production. So this is basically recycling steel in an electric arc furnace. And as I said, the emissions from that EAF portion really vary based on the grid. So we'll say it's about 1/2 ton of CO2 per ton of crude steel. So definitely the lowest emissions of those three options. The reason why we wouldn't just switch everything to scrap-based steel production is that scrap is limited. It can be challenging to reclaim steel scrap. There's a whole supply chain there, some different issues. So when we're talking about decarbonizing the steel industry, the main options are to increase the recycling and scrap. As I just said, there's a few challenges there. And then there's also some innovative steelmaking technologies that are set to come online in about the next decade. The first that's really promising is hydrogen-based DRI. So this is using hydrogen as your reducing gas in the DRI unit. And if that hydrogen is made with 100% renewable energy, it is possible to basically make zero emission steel. And that's really the most promising option for low emission steel making right now. The most recent announcement for a commercial scale plant, I believe it was yesterday, Arcelor said that their plant in Spain is projected to reach commercial levels by 2025. So this technology is coming online. It's not quite there yet. The other option is to apply carbon capture, or CCS as we call it, and that can be done with the blast furnace basic oxygen furnace route. Although, like I said, there's process emissions because you're using coal as a raw material, so you're never going to achieve zero emissions like you might with the hydrogen-based DRI. You can also apply the carbon capture storage to the natural gas DRI production, and that can get you much closer to net zero. So again, here's a table of the emissions intensities for steel production, I just want to emphasize again, you have, most steel right now is made by the blast furnace basic oxygen furnace route. And then the electric arc furnace routes tend to be lower emissions unless you're looking at the coal-based. So why do we care about this? Well, steel is responsible for 11% of global carbon emissions and 7% of global greenhouse gas emissions. Multiple reports have come out recently showing the pathway that the steel industry could take to reach mid-century net zero targets. And, whichever group you're looking at that has come out with these pathways, what's clear is that the steel industry needs to make a shift from how they're currently operating to achieve any of these goals. And the way that that's going to happen is switching away from the blast furnace basic oxygen furnace steelmaking route, using more of these innovative low emissions technologies like the hydrogen-based DRI and carbon capture storage, increasing scrap recycling, material efficiency, so smarter design in steel. And then, this transition is going to be driven by green steel demand. Steel plants aren't operating with huge margins of profit. So in order to be making investment decisions to move towards lower emissions steelmaking, there needs to be green steel demand that shows these steel manufacturers that folks will be purchasing this lower emissions steel. And that's where sectors like the oil and gas industry can come in. So oil and gas infrastructure, steel pipelines are the main material used in gas transmission networks. So crude oil, acidic bearing fluids, and the other petroleum products used in oil and gas are really corrosive and create a lot of thermal stress and structural stress on pipelines. So you need a really strong material like steel. Although stainless steel is, more resistant to corrosion than carbon steel, it's also much more expensive. So carbon steel is the main material used. Now the pipeline market is set to grow by about 6% annually from 2021 to 2026. We are seeing, more pressure to move away from oil and gas. So that could change. But I think it's clear that there's a lot of projects in development. I'm going to go through a little bit of that in a moment. And then there's also a lot of cases where oil and gas pipelines are being repurposed for other uses. For example, the new hydrogen economy. We have over 1,000 kilometers of pipelines being used for hydrogen in the US. In the EU, there's a lot of projects going on to convert oil and gas pipelines for hydrogen transport. They're predicting 23,000 kilometers of pipeline being used for hydrogen by 2040, and about 3/4 of that is repurposed natural gas pipelines. So whatever's happening with the oil and gas infrastructure, we know that pipelines are being built, and that steel demand is coming through. So according to our infrastructure tracker for oil and gas, we know that there's about 1 million kilometers of gas pipeline currently operating and about 250,000 kilometers of oil pipeline currently operating, and then over 200,000 kilometers of oil and gas pipeline in development right now. And using some standard characteristics of pipeline, that equates to around 37 million tons of steel that will be demanded for these pipelines. So that's a pretty big amount of steel that could be sourced with conventional methods, or it could be sourced with green steel. So last fall, the World Pipelines Report, which is a technical magazine supporting the oil and gas industry, they made this call for the oil and gas industry to support the transition to a low carbon economy by sourcing oil and gas pipelines from carbon neutral steel producers, which is a pretty big call to action for the oil and gas industry and led to a lot of questions for us. Initially you might say this seems like a moonshot, but the IEA Net Zero 2050 report found that oil and gas companies are responding to pressure to invest in clean energy. So I think there's also an opportunity to pressure them to invest in green materials and see them respond. So the main questions we had coming from this report and the status of oil and gas infrastructure is what role can and should the oil and gas industry play in driving the transition to low emission steelmaking? How will sourcing green steel affect the overall cost of a typical US or Canadian oil and gas pipeline project? And then what tools does the government have to intervene and help support this transition? So I just want to take a moment first to talk about green steel demand. So we know that low emission steel production is essential to meet mid-century climate targets. Embodied carbon emissions are being identified and valued through mechanisms like carbon border taxes and policy levers. So demand signals from steel buyers are needed to drive the green steel transition. So steel buyers need to cover the green steel premium to drive manufacturers' investment decisions. Because steel manufacturers need to know that buyers are committed to buying large quantities of green steel for the long term. And this is important because, as I said before, these low emission steelmaking technologies haven't reached commercial scale yet, but they're set to in the next 5 to 10 years. And at the same time, steel plants are facing these reinvestment cycles, and most steel plants are going to be making decisions about reinvestment cycles and whether to prolong the units they currently have operating or to replace them with lower emissions steel manufacturing units in the next 5 to 10 years also. So the oil and gas industry, could help create this green signal demand or this green steel demand, signaling to steel manufacturers that interest and investment in green steel is serious. And, that could help drive a big transition in the steelmaking technology currently used. So there's a group, the Mission Possible Partnership, out of Rocky Mountain Institute and the Energy Transitions Commission, that put out a great report recently, Stealing Demand, that looks at different sectors and their potential to support the green steel transition. They did not identify oil and gas as a, having really high potential for driving the green steel demand, primarily because decarbonizing materials in the supply chain is not a priority for that sector. However, I would go back to that IEA Net Zero 2050 report that showed that oil and gas is responding to pressure for clean energy and technology investments, and say that, green materials could be next. So I think that there is some potential there. Now, we did a little case study looking at the cost that sourcing 100% green steel would add to a typical pipeline project. So using some standard characteristics of steel pipelines used in oil and gas projects, we found that the total cost increase to a pipeline is around 7.5%, or about $75,000 per kilometer. And the carbon dioxide savings for that switch, if you're looking at, say, blast furnace, basic oxygen furnace steel to green steel, would be around 276 tons of carbon per kilometer of pipeline. And the cost of that is about $272 per ton of carbon. So what does that tell us? It means that oil and gas is not going to be making this transition to purchasing green steel on their own. The economic incentive isn't there based on what we see in carbon pricing. So this wasn't an overall shocking result for us, but we still were thinking about ways that the government might be able to get involved and help drive that transition. And there's quite a few options. So one would be to consider embodied emissions in pipeline applications. There's also the potential of using green public procurement policies for state-owned oil and gas pipeline projects. Of course, that's not super relevant for the US or Canada, but there are places where that could make a big difference. There's also the option of setting Scope 3 emission standards under the American Petroleum Institute standards that are used for sizing and safety criteria for pipelines. And then I think there's also a big potential for phasing out oil and gas pipelines by requiring repairs and remanufacturing of corroded steel pipes rather than replacement. So that's really working under the material efficiency umbrella and lowering steel demand. I also wanted to give this example plant in Canada. It's a blast furnace basic oxygen furnace facility with about 3 million tons of crude steel capacity per annum. And this plant primarily produces large diameter pipes for the oil and gas industry. And they recently received around 16 million Canadian dollars from Canada's Strategic Innovation Fund to upgrade the facility. So that was a huge investment in this steel plant, but really an investment in the oil and gas industry. And this money is currently being used to make some improvements to the plant. But if this model were used where the government invests directly in steel plants to upgrade the technology and cover that green steel premium, that's a way that the government could be supporting the transition to green steel making and driving green steel demand so that it's affordable for these oil and gas projects. So we're also going to be looking in coming days at other sectors and how they could be driving demand for green steel. And a really promising one is looking at the renewable energy sector. Unsurprisingly, there's a lot of incentive for them to be sourcing green materials. We know that the US and EU will be requiring around 5 million tons of steel by 2030. That is significantly lower than the 37 million tons that we see in the oil and gas industry, but still a large portion. And the exciting piece here is that this Mission Possible Partnership report found that for renewables, whether you're looking at offshore wind, onshore wind, or solar, it adds less than 1% to the final product cost to source green steel. So that means that you could have consumers paying that green steel premium without causing an issue for the project developers or the utilities. So we see a lot of potential there, and we're going to be doing a series of these case studies for different sectors, figuring out where the opportunities are to drive green steel demand. But I'd say in the end, the oil and gas industry is going to be demanding a lot of steel, and there are opportunities to make sure that steel demand is supporting the green steel transition. So I'll end it there, and we'll be taking comments at the end. Thank you.
Thank you very much, Caitlin. That was a really unique perspective and big challenge indeed. We're going to move on to our final presenters. We have two presenters talking to you a little bit about the Shakespearean dilemma of to co-digest or not to co-digest. That is the question of the hour. A little bit about Sabarish Vinod and Kyle Crete. Sabarish is a director of new product and services at Linkis Inc., where he leads their expansion into new markets and in the design of new offerings. His focus is on driving development of solutions that break down barriers to customer participation in energy efficiency programs. He has provided technical and policy support for energy efficiency and demand response programs as a subject matter expert on complex technologies and system optimizations. Sabarish has a patent pending on the remote pump monitoring device for oil and water pumps. He holds a bachelor's degree in mechanical engineering from University of Calicut in India, and a master's degree in mechanical engineering from the University of Michigan, Ann Arbor. Kyle is a project manager for the Energy Coalition and is also a mechanical engineer from Cal Poly SLO. Kyle joined the Train Company in Los Angeles as an account manager focusing on commercial real estate and large entertainment facilities. Kyle helped them maintain and upgrade, replace aging equipment and controls to improve their facility operation. After 5 years with Train, Kyle moved to Climate Tech in Orange County as an account manager, focusing on the West Side LA market. He has furthered his experience in building automation systems and other facility types, including schools, hospitals, and multifamily residentials. He also has a MBA at Pepperdine University. Without further ado, gentlemen, it's your turn to present.
Thank you, Siddhika, for the introduction. Let me share my screen here. Okay, so it's up. So welcome everyone to the presentation. As Siddhika pointed out, we are looking at co-digestion in wastewater treatment plants using anaerobic digesters, and using that perspective to see what can we do about landfill organic waste diversions. So I'm joined by Kyle Crete here. We will be examining this topic along with some of the basic questions regarding what is co-digestion, what is the landfill organic diversion need. So we'll be setting the stage there, understanding the problem, defining the boundary conditions, and from there we'll figure out how to set up the problem such that we provide a framework for different agencies that will be interested in pursuing co-digestion for their plants. So as I explained earlier, we'll do the introduction to the topic. We'll look at the current state of emissions, waste characterization, and we'll go into this a little bit more detail as we go into the presentation. The current state of market, what does it look like for co-digestion right now? What does it look like for landfill diversions? The beneficial use of biogas, some rate analysis, scenario analysis, that is to look at different approaches that we use in our analysis to figure out when does co-digestion make sense for an agency when they are trying to pursue it. Okay, so first of all, so what is co-digestion, right? So co-digestion, it refers to the practice of digesting organic material from multiple sources in an anaerobic environment. So when you look at a wastewater treatment plant, for example, there are studies that show that there's 10 times energy contained in a wastewater that's going into a facility than what is required to treat it. So there's a lot of energy that goes into these plants, but it is not utilized. Specifically with the plants that are equipped with anaerobic digesters, it provides a really good opportunity for the plant to recover some of that energy. Now, co-digestion. So when you think about a wastewater treatment plant, it's typically treating municipal or domestic solids that come into the plant. Now, by adding organic material from additional sources, what that does is that increases the biogas yield from existing digesters. Now, increasing the biogas yield, it offers pathways for beneficial use of organic waste that is otherwise then sent to landfills. But then the flip side of that is that co-digestion is very expensive because it requires a lot of infrastructure to be in place. It requires a lot of personal training so that they are able to handle all the additional equipment that is necessary to collect this waste, process it, and then finally put it to beneficial use. And then it requires favorable regulatory policy. And we will go into this details a little bit later as we go into the analysis. Now, why is this important, right? So when you consider the state of emissions right now, what we are talking about is methane emissions. And methane is the emissions from municipal solid waste landfills accounted for 15% of total US methane emissions in 2018. And this is based on a study that was conducted by EPA. And when you look at it further from a volumetric standpoint, the landfill gas, as it is called, it accounted for about 2,400 standard cubic feet per day. And when you consider that the composition of a landfill gas, 48% of landfill gas on an average contains methane. I mean, that is by volume. So we are talking about 1.2 million standard cubic feet of methane being released into the atmosphere. Now, all of that is not bad news, and I'll go into that a little bit later. But with methane, though, the problem with methane is that the global warming potential of methane is at least 28 times higher than that of carbon dioxide. Now, that's where the problem comes in because of the higher global warming potential of methane. As I explained earlier, all of this landfill gas is not being released into the atmosphere. Some of it is being put into beneficial use. And based on available data by EPA, they collect all this information. About 48% of the landfill gas is not put to any beneficial use. So that poses a significant opportunity and a challenge for all the stakeholders to act in terms of figuring out how do we make use of this resource here. And what is causing these methane emissions, right? So methane emissions are a result of organic decay. And going into the next slide, food and other organic material, they form the single largest category of waste directed to landfills. So to sum this up, there's a lot of methane that is being released, that is being generated in landfills. A good portion of that is not being used, put in any beneficial use. And that methane is the result of organic decay, which comes from organic food and organic material that is being sent to landfills. So what does that look like, right? So how do we characterize this waste? So organic waste, it accounted for 24% of all municipal solid waste that was sent to landfills. And industrial, commercial, and institutional customers accounted for more than 75% of this waste generation. This is important to consider because when you have a concentrated group of customers that is sending this type of a waste into a landfill, that means that there is an easily addressable solution or easily addressable problem where you're able to figure out how do we collect this organic waste, how do we process this, how do we make sure that this organic waste is not being dumped in landfills, which results in methane emissions, which has 28 times the global warming potential of carbon dioxide. Now, here is a table that shows the organic waste here, right? So just looking at these numbers, in the year 2018, this is in 1,000 metric tons. So about 63 million tons of waste was generated. And then about 35 million of that was landfilled. So we are talking significant potential here in terms of, or significant opportunity here in terms of capturing, being able to capture this organic waste that is being sent to landfills, which sits there, it decays, produces methane, a large portion of which is not being put into any beneficial use. So how do we do this, right? So when you consider this organic waste and co-digestion, as it was explained earlier, we are figuring out a structure by which, or infrastructure by which, we are taking this organic waste and sending into facilities that is able to collect this waste, process it, and then the resultant higher gas yield can also be put to beneficial use. So naturally, when we were thinking about landfill diversions, we are thinking about wastewater treatment plants, right? So we are thinking about wastewater treatment plants that are equipped with anaerobic digesters. Now, there are 14,000 wastewater treatment plants in the US. We need to be able to figure out a solution where, we need to figure out how many of them are equipped with anaerobic digesters, because that is one of the requirements for plants to receive organic waste, process it, and then produce biogas as a part of it. So to figure that out, we used available database. The one that we went to is the Water Environment Federation to locate plants that are equipped with anaerobic digesters. And then we had to, we collected the data from the Water Environment Federation database, but then just to make sure that we are using good quality data. We cross-check that data with the other databases that's available. So in this case, we use the EPA Clean Watersheds Need Survey database, which is maintained by the EPA, and it contains information regarding wastewater treatment plants, the technologies that they employ. And to discuss some of the quality, the data quality checks that we did, I pass this on to Kyle.
Thanks, Sabrish. Yeah, so we cross-referenced these two databases. The first being the Water Environment Foundation, and the second being the EPA. And what we were looking for was we wanted to make sure that we had at least a 90% confidence level with 10% precision as we were running our calculations and to do so. So Sabrish, you can go ahead and share the rest of this slide that's on there. And you know what we found was, as you know, these were the numbers that we came up with, and we ran them through these two formulas in order to come up with this magic number of 91 data samples to verify between the two databases, and just to cross-reference the two to make sure that we had the right set of data and that it was accurate. So moving to the next slide there. So looking at our quality, our quality control, what we found was, of the 91 samples that we used, and then we used a random number generator to make sure that we were being unbiased in our research. So we took 91 random samples from the 1,268 wastewater treatment plants. And we found that 67%, or 61 of the 91, matched perfectly between the two databases. So we were very happy with that. Of that, we found the remaining 30 were inconclusive. And this was for, a number of reasons. So 13 of the entries had incomplete data set from the Water Environment Foundation. So with that, we were able to cross-reference in the EPA's database to get those numbers as well. Now, 11 of those had incomplete data from the EPA, so there was not necessarily too much we could do about that. And then finally, the remaining 6 were just missing some data from both entries, and it was usually, one or the other. So we were primarily concerned with average daily flow versus design flow. So several of these had with the EPA, it may have had a permitted flow rate or design flow rate, but it was missing the average daily flow. So we had to combine the two in order to really find the most accurate data that we use. So that was a little bit behind the scenes and what our thinking was going through this.
Okay, thank you, Kyle. So using the data that came from the Water Environment Federation, we looked at what is happening right now in the industry. Okay, is the biogas that is being generated in the wastewater treatment plant being put to good use? And there are different uses to biogas, right? So one example that's shown on the screen right now is what we call a direct use. So direct use of biogas is where it is being used to drive turbo machinery, it's being used to drive pumps, it's being used to drive blowers. In some cases, they were being injected in the pipeline. In some other cases, they were being used in HVAC systems. But a lot of the direct beneficial use of biogas is to heat digesters. And on the flip side, on the indirect use of biogas, where biogas is being used to run a machinery, run an equipment to generate electricity. So that is the indirect use as we define it. And from these graphs, you can see that more of these charts are the color orange, which means that there is not much beneficial use going on. So so it's not that common, right? So beneficial use of biogas, even with plants that are equipped with anaerobic digesters, that is that is creating biogas using domestic waste is not that common. And then production of electricity using biogas is not that common either. So there are a lot of considerations when you look into why that is the case, right? So some of the things that we came up with is that in a large part of the country, the electric and the natural gas rates are not that significant, right? So it doesn't justify the investment required for additional equipment that is required to treat, process, and put the biogas to beneficial use. So electricity and gas rates, and we'll go into this a little bit later, and because the payback on the investment is being justified using offsetting electric use or gas use at these plants. And total biogas yield is also a factor there. So because based on the analysis that we completed, a plant that is producing, or the plant that is treating about 20 million gallons per day is required to really, that is the sweet spot where plants can invest in equipment that will take the biogas, treat it, and put it to beneficial use. And not a lot of plants meet that criteria. And then because total biogas yield is also a factor, co-digestion works really well here, because one of the factors that co-digestion does is that it drives up the biogas yield from these facilities. But then once you take the organic waste from landfills and treat it in a wastewater treatment plant, you still have to dispose of the solids that come out of these digesters. And proximity to landfills becomes a factor, because if the solids that are coming out of this digester have to be sent to a landfill, you have to look at the economics there as to, does diversion make sense? Is the landfill close enough that any type of emission savings that I get is offset by the trucking that's required to take the solids from wastewater treatment plants to the landfill? So electric and gas rates are important, like I mentioned before, and I'll pass this back on to Kyle to discuss some of the analysis that we did to look at what does it look like, what does the rate look like throughout the country.
Yeah, so for our analysis here, we used the U.S. Energy Information Administration's analysis for their electrical rates. What we found was the weighted average price of electricity is about 7.5 cents per kilowatt hour is what we found. And of course there were some outliers in there, such as Hawaii and Alaska, and a lot of that is due to the logistical challenges there. But ultimately the industrial sector prices have increased by more than 10% in 7 states. And then on the other hand, you had a greater than 10% decrease in 4 states. So evaluating the most cost-effective use of biogas generated at wastewater treatment plants really requires that careful consideration into the variable costs of electricity. In a state such as Washington, where 75% of the electricity comes from hydroelectricity, electricity generation, it may not make as much sense. So it's really important to keep an eye on this. And if electricity prices decline, non-electrical applications for biogas may be preferred, whether it be heating the digesters or using it to run equipment. But on the natural gas side, we see a general downward trend in prices. Now, without getting too political, it could have had something to do with administration over the past few years. But the average price of natural gas has dropped during the past 5 years. So the weighted average of this price is about 48 cents per therm. Here, the national average is 59 cents. But I'd like to look at the weighted average a little bit as well. So there's also, with natural gas, there's a significant price difference between states. As you can imagine, you have states such as Louisiana, Oklahoma, where there is just a tremendous amount of natural gas at their availability. So it may not make as much sense to implement these co-digestion projects there. As with electricity, the cost of natural gas will play a significant role in justifying, from a business standpoint, whether or not co-digestion projects are really worth it.
Thank you. So with that background, with what the co-digestion is, what we are looking to implement co-digestion, what are some of the governing factors that will determine the success or the failure of a co-digestion. We looked at 3 different scenarios. We looked at 3 approaches. And what we did here is, because each plant is unique, so each wastewater plant is unique, they have their own requirements, they have their own equipment, they have their own infrastructure. So what we did was we looked at a representative project that we did in California. And using that project as our basis, we evaluated the scenarios, right? So approach 1 that we looked at is a conservative outlook, and then assuming that it's 35% success rate. So what that means is that based on the capacity of the equipment that is installed, the plant is only seeing that the equipment is operating at 35% capacity. And what this means is that the plant is not actively pursuing, it's a passive approach where they are talking to their community to get as much organic waste sent to the plants as possible. The second approach is a little bit more aggressive on the plant side, where it is operating at 67% capacity. So this could mean that the plant is actively working with local restaurants to figure out, okay, what are they doing with their fat, oil, and grease, right? Or they could be talking to the ag community to figure out what are they doing with their organic waste. And the third approach is a very aggressive approach where the agency is sourcing out as much organic waste as they can get their hands on to make sure that the plant is operating at 100% capacity. And it matters because, again, as I mentioned earlier, total biogas yield is a significant factor in making sure that a co-digestion project is a success. And all these projects, all these approaches, the 3 approaches were evaluated under different scenarios for energy cost and borrowing rates. And further, to normalize the analysis across different plant types, we came up with this benefit to cost ratio was considered rather than using simple payback, because simple payback may not make sense for comparing different plants. So benefit to cost ratio for the purpose of this paper and presentation is defined as the net present value of the co-digestion project over its life divided by the initial cost. So we, for our analysis, we assumed that the life of the project is 30 years, and then the initial cost again is being derived from our representative project, but then it used some of the standard cost guidances for the purposes of estimating total capital cost required to implement co-digestion. Now, one thing that I'll say here is that we are not trying to attempt the size of the market. The cost should be considered concept screening. Again, costs and benefits will be highly site specific and should be independently evaluated for each site. Okay, now getting into the economic analysis. As I mentioned earlier, we are using a representative project to estimate benefit and cost. Cost considerations are based on EPA. There is a model that they put out, the EPA Food Water Biogas Economic Model. So it goes into detail regarding what type of equipment is required, depending on the size of the plant, the scope of the co-digestion project. We can estimate what is an approximate cost to implement co-digestion at the facility. We then fully discounted any tipping fees to account for additional maintenance and personal costs. So One of the things with co-digestion is that it is another revenue stream for wastewater agencies, because now as the organic waste is trucked into the facility, these agencies can charge tipping fees. So we discounted that, because once this equipment is in place, they'll have to hire additional personnel. They have to make sure that it is maintained properly. There's salary required for this additional personnel. So to account for all those additional extra costs, we discounted it. And we further discounted the power generation by 30% to account for cannibalistic loads, such as scrubbing of the biogas to make sure that it meets pipeline standards, equipment required to inject the cleaned biogas into the pipeline. And then we assumed a financing rate from 0% to 5% and a 15-year loan term, and used a 30-year life for the equipment to estimate net present value. And as Kyle pointed out earlier, we are using these national averages that we were able to estimate using information from EIA. Okay, so coming to the results. So if you are using biogas for power generation and heating, so this is like a combined heat and power type of a scenario. We found out that approach 1 is not cost effective under any scenario. Now, approach 1, if you remember, is the least. So that is a very passive approach by the agency, where they are taking what is being delivered into the facility. They are not actively sourcing out organic matter for co-digestion. So as a result, there is not much additional biogas yield being produced. And because the benefit is from the additional biogas that is being derived, approach 1 does not see any benefit. So in the chart here, so this is benefit to cost ratio, and this is the interest rate, borrowing rate. So if it is less than 0, then that means that it is not cost effective. So again, just to drive that point again, approach 1 is not cost effective because it is not resulting in significant additional gas yield. So to look at other scenarios, we also evaluated renewable natural gas. So what is renewable natural gas? Renewable natural gas is where the biogas is being cleaned to utility standards and injected into the natural gas pipeline. So in this scenario, there is no power generation. So the cost of power equipment is discounted for this analysis. And then approach 1 is only economical in 2 permutations, so low interest rates and high energy rates. So it became economical because the cost of power equipment was discounted. So it's only economical in 2 permutations. So we are not even considering that. Okay, so because we are talking about natural gas, the energy costs were considered for gas only, and energy rates for gas from 59 cents per therm to 80 cents per therm were considered. So here are the results. Approach 2 is the slightly more aggressive approach, where they are going out there making sure that the equipment is operating at least at 67% capacity. So as you can see, even in this situation, at higher borrowing cost rates, some of these scenarios are still not cost effective. And in approach 3, where they are, it's a very aggressive approach, they are making sure that the plant is operating at 100% capacity, then it becomes cost effective under these various scenarios. So what does this all mean, right? So just getting to the conclusion side of it. Co-digestion is a promising and an achievable solution for addressing emissions from landfills. There is a certain science that has been already investigated. People understand this, but it is not that commonly used. Barriers exist in terms of available technology. Trained personnel is a big barrier. because they need to make sure that they hire people that are trained and they are able to maintain the specialized equipment. Proximity to landfills, available capacity in existing wastewater treatment plants. So if they are operating their digesters at capacity right now, then there is no way we can send additional organic matter. So that means that they probably have to add additional digesters, and that increases cost. Flat trends in energy prices and relatively low energy price, it makes it harder to justify co-digestion projects unless strategies are put in place to ensure that there is high levels of capacity utilization to make these projects successful. And also source separation of organics. So this is making sure that the organics that are being delivered into the plant is free from debris, it's free from foreign material. It is something that the plant can directly use within their process. And finally, the RNG prices, renewable natural gas, because a lot of the gas companies are looking at improving their portfolio by adding renewable natural gas to their portfolio. So some gas companies may be open to negotiating higher RNG rates with the wastewater treatment plant because they are looking for a renewable portfolio. And then finally, low or zero interest rate loans may help justify the project. So this is where regulatory support is required. This is where support from the government is required to make sure that we are addressing this at multiple levels. So finally, to wrap up everything, co-digestion does offer a promising solution, but then it requires effort from the agency that is participating. It requires effort at the local government agency. It requires effort at the industry as a whole to make sure that such agencies where they are showing interest get supported. And then also there is support at the federal side to make available low or zero interest rate loans so that they can justify these projects. So that's it.
All right. Thanks to all of our presenters for a real thought-provoking perspective and out-of-the-box ideas being discussed. I think we're gonna bring the presenters back, but in the meantime, please, audience, if you have questions, go ahead and use the chat box to send us your questions. We've collected some throughout the program, which I'll go ahead and ask the presenters. Welcome back. So we'll start with you, Andrew. The first question is for you. Could the SEM assessments be targeted to reach more small and medium-sized plants? These make up hard-to-reach segments of the industry that have a considerable amount of carbon footprint when looked at the whole segment. So they're numerous and widespread. So what can we do on the SEM assessments?
So we found, firstly, that industrial energy efficiency programs, at least in North Carolina, have traditionally catered to small and medium-sized companies. So we wanted to access the opportunity presented by large C&I customers in our analysis. The Department of Environmental Quality's Environmental Stewardship Initiative focuses largely on to medium-sized plants. We also found that to evaluate things, we needed a threshold for eligibility for successful participation in an SEM program. And we found that 1 million kilowatt hours in energy consumption would be an appropriate threshold for that participation, which is the same threshold for opting out from utilities EE riders. So the opted out load we determined served as the eligible load from which we found savings potential. But you're right, there to reach that small and medium-sized part of the sector. So there needs to be SEM pilots focused on workforce development, firstly, to overcome the barriers that have historically hindered small and medium-sized facilities from implementing energy management strategies due to the cost of services relative to potential savings, the lack of capacity to monitor energy and maintain savings, and the inadequate workforce to accommodate transitions. But SEM should be entirely possible for really highly motivated small and medium industrials with a cohort approach, especially. It was just not in the scope of our analysis, and is another point towards our savings estimates for the potential of industrial energy efficiency to reduce electricity demand being relatively conservative.
Thank you for that answer. Next, we'll go to Caitlin. A question to you is, the U.S. infrastructure uses huge amount of steel in reinforced concrete, structural steel, and piping, often with Buy America requirement. With the bipartisan infrastructure framework getting a lot legs in Congress, how about using it as a catalyst for pushing green steel and green concrete? Is that happening?
Yeah, that is a great question. And there is indeed a movement for buy clean policies. I'm not sure that we're actually going to see it in this infrastructure bill, or on what level we'll see it. But that definitely is a policy tool that's being used. What I am seeing, because the U.S. Steelmaking industry, it's a bit flipped from the rest of the world. So we have about 2/3 of our steel production occurring with the electric arc furnace steelmaking unit, whereas most of the world, it's about 2/3 for the blast furnace, basic oxygen furnace. And like we talked about, the emissions intensities for EAF production is lower. So there's an argument that sourcing American steel means lower emissions steel, but it's not quite the same as green steel. And so I think when you're looking at actually driving the green steel transition, we still need to see more investment from the government in green steel making technologies to support that transition. And I mean, until these technologies reach commercial scale, it is going to be tricky to figure out how these public procurement policies can work, requiring purchasing through lower emission steelmaking technologies that are available right now, like the huge amount of EAFs in the US, is a good place to start. But ultimately, that's not quite far enough.
Understood. There's a follow-up question to you. It was really interesting to see the renewable energy sector angle in your presentation. One of the audience wants to know, what is steel used for in the renewable energy sector generally?
The big one is wind turbines.
Got it.
They're made with steel. So.
Got it. All right, let's move to Sabarish and Kyle. Question for you is, what is the potential of biogas to be leveraged to create a teal mix of blue, green hydrogen for industry and transport? And does that actually enable better return on investment for these projects?
So from a hydrogen standpoint, what you need to do is you have to have a really good, very clean natural gas coming in, right? So if you are able to get to that type of scrubbing with your natural gas or the biogas that's coming out, I'm sure, I mean, that there is that potential. We have some plants in California where they are actually converting the biogas into renewable natural gas and feeding into fuel cells. So this is a technology that is currently being actively pursued by agencies. So definitely, but then again, the challenge is really making sure that you get it to that real clean pipeline quality.
Got it. And this is a follow-up question that's addressing some of what you're just saying. Are there barriers besides economics to renewable natural gas from co-digestion being injected into the pipeline?
Yeah, definitely lack of trained personnel is a big barrier, right? So there needs to be personnel available at each of these wastewater treatment plants, that they know how to maintain the equipment, that they are doing it on an ongoing basis, So lack of trained personnel is definitely a big barrier other than economic. And then there is also competition from the private industry right now where they are actively going after, which is a good thing. I mean, it is a good thing that there is competition, that they are actively going after organic matter. So these private agencies are trying to build their own anaerobic digesters, convert that into biogas, and then provide that as renewable natural gas. And there
Yeah.
are standards.
Yeah, I'll add to that, Sabrish, that the quality and the purity of the gas that needs to go into the pipeline is very important. And the equipment, to clean the gas well enough to be injected into the pipeline, adds to that capital cost and the maintenance and ongoing training for the personnel as well. So there's that purity is a big barrier as well.
Understood. This is a question regarding greenhouse gas accounting practices. Caitlin, the question is if there are policies for accurate greenhouse gas accounting for green steel to create a level playing field for all manufacturers.
Yeah, there are some different options. So, this can be done again because I said, a lot of it depends on the electricity grid. That really influences when you're talking about using an electric arc furnace. The grid mix is going to be a huge component in the emissions. So whatever accounting they can do for the grid mix would apply to the steel. And then there's options for doing greenhouse accounting, going on a technology level. So knowing like certain pieces of technology, if you make it through this route, it's going to have this average emissions intensity. But I haven't actually studied up on actual ways to measure. The answer is I'm not quite sure. But it is very clear, like the difference in emissions between these different processes is so significant that it would still be quite easy to set up some sort of like levels for emissions just based on the process that's being used. You would know a significant amount of savings that way.
Understood. We've got a couple of more questions coming in. Cleaning the biogas to pipeline quality is important, but we work with natural gas distribution. And so, distribution. So don't see it as a big barrier, just part of the process. Do you agree with that? Okay.
It's a part of the process, but as Kyle pointed out, it's an expensive part of the process.
Got it. Going back to Andrew, what are the factors from adoption standpoint, having a carbon pricing as an incentive mechanism within the states to get more participation from customers who are opting out from some of these state programs?
Yeah, so I think as the North Carolina case demonstrates, any opportunities to combine federal funding to IACs with state and or local funding should be explored, as mature centers can typically find more assessments to perform with additional financial support. So pairing IAC funding with other decarbonization measures, including a carbon pricing or a cap and trade program to reduce industrial emissions and motivate clients to seek out savings, access through industrial assessments could be really impactful.
I know time is of the essence, so I'm going to finish this session out with the last question here. Were you able, this is for Sabrish and Kyle, were you able to estimate how much renewable gas the U.S. can produce annually and how much capital would be required to integrate co-digestion into wastewater treatment plants that are closely located to landfill?
We have not estimated that market size. But then to answer the second part of that question, what we found out is that the minimum threshold to entry is $5 million. It's about $5 million. So per plant.
And has the cost of the technology to co-digest gone down over the past, 10, 15 years? What's it?
It has definitely gotten better, but then again, the problem is that with co-digestion, you need different technologies along the process. So you need one to collect it, you need one to process it, and then even with the source, right? So you have to prepare the organics for introducing into the digester. So there's a lot of pieces to it, and that adds up pretty quickly.
Yeah, for one particular project that we're working on, doing this study for an EPA grant, we found that the whole process, setting the whole project up, would be somewhere between 10 to 14 million, and that's from source to gas.
Great. Thank you for all of your participation and answering the questions from the audience. If we have any questions that are unanswered, we will make sure that it gets back to our speakers for response. Thank you to the speakers. Thank you to ACEEE for this great topic. And we look forward to seeing you in another session tomorrow. Have a wonderful day, and we'll wrap up.
Thank you.
Thank you.